All right, if you've ever written code in, Java or Kotlin, you have definitely hit this crossroads. Should I use an array list or a linked list? Well, get ready because we're about to dive into a performance mystery that flips pretty much everything you learned in computer science class right on its head.
So this whole thing kicks off with a question from a developer on Reddit, and man, it just perfectly captures the confusion. They ran a test, fully expecting linked list to be the big winner for insertions, but the results were the complete opposite. It's a frustration a lot of us have probably felt.
So, what exactly did they do? Well, it was a pretty simple benchmark. They just wanted to see how long it would take to add almost 1 million elements to both an array list and a linked list. And the results? Well, they weren't just surprising. They were, honestly, kind of baffling. Okay, get a load of these numbers. The array list clocks in at around 223 million nanoseconds, but the linked list, a whopping 683 million. That means the array list was nearly 3 times faster at the one job linked list is supposed to be amazing at. So, what in the world is going on here? And this right here is the question that just makes your brain short-circuit. Everything we've been taught, all the textbooks, they all tell us that inserting elements should be linked list superpower. So what's the deal? Could the theory we all learned just be wrong? To really get why this result is so mind-bending, we gotta do a quick rewind. Let's go back to the basics, the textbook theory, and remember how these two data structures are actually built under the hood. First up, the array list. The best way to think about this is like a perfectly planned street, where all the houses are built right next to each other in one long, neat row. It's a single, continuous block of memory. This makes it super fast to jump to any house, as long as you know its address, or, its index. A linked list, though, totally different story. This thing is more like a chaotic treasure hunt. Each spot, or node, has two things. The treasure, that's your data, and a clue, which is a pointer telling you where to find the next node. And these nodes can be scattered all over the place in your computer's memory. And right there, that's the core difference. Array list is organized, it's sequential. Linked list is all over the map, just connected by these pointers. This one structural difference is the key to this whole mystery. So, the textbook theory goes like this. Adding an element to the middle of an array list is slow. In big O notation, we call this O of n, because the time it takes grows with n, the number of elements you have to physically shift over. But with a linked list, you just change a couple of pointers. That's supposed to be a lightning-fast O of 1, or constant time operation. It should take the same amount of time no matter how big the list gets. That's the conventional wisdom anyway. But here's where we find the first clue that starts to unravel this whole thing. The original test had a bit of a flaw, and it all comes down to where you're actually adding the new element. Turns out, not all add operations are the same. Yup, another developer on Reddit jumped in and spotted the issue right away. The test code was using list.add, which doesn't actually stick an element in the middle. It just tacks it onto the very end. And for an array list, that makes all the difference in the world. You see, for an array list, adding to the end is super, super cheap. There's usually some empty, pre-allocated space just waiting for a new element. But inserting at the beginning? Oh man, that's the absolute worst case scenario. You have to shift every single element down by one just to make room.
Okay, so you're thinking, aha, the test was just wrong. Case closed, right? But hold on, it's not that simple. Because here's where the mystery gets really weird. Even when you run a proper test, one that inserts elements right into the middle, the array list still often wins. So how on earth can shifting millions of elements be faster than just changing a couple of pointers?
It turns out the real answer has almost nothing to do with abstract data structure theory and everything to do with the actual physical hardware inside your computer. The key to this whole performance puzzle isn't the data structure itself, but the CPU and how it talks to memory. And this comment from another user, it just hits the nail on the head. The biggest performance killer isn't the algorithm. It's the time the CPU spends literally just sitting there, waiting for data to arrive from main memory. And this is where something called a cache miss becomes the ultimate villain for our poor linked list. So here's the deal. Your CPU has this tiny but incredibly fast piece of memory right next to it called a cache. When it needs data from the main memory, which is much slower, it doesn't just grab the one little byte it asked for. No, it's smarter than that. It grabs a whole chunk of data around it, basically betting that you're going to need that nearby data very soon. And this is where it all clicks into place. With an array list, all the elements are neighbors living on that same street. So when the CPU grabs one, it gets all its neighbors loaded into that super fast cache for free. We call this being cache-friendly. But a linked list? Oh, the nodes are scattered to the four winds. For each and every node, the CPU has to go on a new, slow, expensive trip to main memory. This causes constant performance-killing cache misses.
So, when we look at our comparison again, but this time we add this one crucial piece of the puzzle, cache performance, it all suddenly makes sense. Yeah, theoretically, linked list has a faster insert speed. But in the real world, the array list's amazing cache performance totally smokes the theoretical cost of shifting elements. Raw memory speed beats algorithm theory here, hands down.
All right, so let's put it all together. We've seen that the beautiful, clean theories from our textbooks don't always hold up when they meet the messy reality of modern hardware. So if ArrayList is the clear winner in almost every real-world situation, what is linked list even good for anymore? I absolutely love this take. One of the users said they'd use this exact question as a trap in an interview. The textbook answer is about big O notation, but the answer from an experienced engineer? It's that on modern machines, you almost never use a linked list, because that cache inefficiency just kills performance. So let's just nail down the key takeaways. First, theory isn't everything. The hardware you run your code on matters a lot. The array list wins because its tidy memory layout is cache-friendly. The linked list loses because its scattered nodes cause painful cache misses. The bottom line is, in modern programming, you should probably just default to array list. And hey, if you need a queue, don't reach for linked list, look at ArrayDQ instead. Which brings us right back to the original question. So, what is a linked list actually good for? And the simple, maybe a little sad answer is this. Its most important job today is as a teaching tool. It is a fantastic concept for explaining the fundamentals of data structures, things like nodes and pointers and how memory works. And that really leaves us with a bigger question, something to chew on. If the physical reality of our computers has changed so much that it flips our classic theories upside down, is it maybe time we rethink how we teach these ideas to new developers? Should we be talking about the critical link between software and the silicon it runs on from day one? It's definitely some food for thought. Thanks for joining me.